All right, so first we're going to look at over and under estimations. We're going to look at a left, what is called Raman sum. It's the name of the mathematician who came up with this. A left Raman sum is a lower. And then we're going to also look at a right Raman sum. And we're going to do first increasing functions, and then we're going to look at decreasing functions also. So I'm going to put right beside it. And that's your upper, because it uses the upper side of the rectangle on the right of the rectangle. So first we're going to look at increasing functions. Pretend they're all the same. Okay, now how am I going to do that? I've got to make two graphs and then we're going to talk about it, but I want to take the same shape with these dots. So I got to drag them over somewhere else and copy them. But I don't want the rectangles. There we go. Alright, so a left Raman sum uses the point on the corner of the rectangle on the left to start your rectangle from for its height. That's why there's no rectangle here, because if I go across, it's 0. Does that make sense? I could even draw that in right here, and that would be real obvious that my rectangle is 0. Now, if I do a right Raman sum, let me connect these dots because I didn't get that part of my graph with it. If you do a right Raman sum, you start on the right corner of the rectangle and you go towards the left to make the top. Does that make sense? So the corner of the rectangle is always on the right corner, not the left corner. So you get more rectangles that way because the first one on the other one's gone. Alright, so these are increasing functions. Now, let's talk about these rectangles and what it's called when they're all inside or some of it is on the outside. So, this first one, our left Raman sum, where the left corner of the rectangle is touching the curve, this is called inscribed. Can somebody tell me why they think that's called inscribed? Correct. Right. Your rectangles are inside. That makes it an under estimate, because you're missing a little bit under that curve. Now, obviously, the other one's an overestimation because it's hanging out. But what's it called when your rectangles aren't all inside? Well, that means you have to know what the opposite of inscribed is. It's a geometry word that y'all probably have heard before, but I don't know that you would have thought of it with this. That's right. It is. It's circumscribed. Circumscribed means that it's about the curve. And so, in other words, the curve is inside the rectangles. We think of circumscribed like I have a circle and my figure is inside my circle. So the square is inscribed inside the circle, or the circle is circumscribing the square. Does that make sense? Because the circle is outside of the square. The whole square is inside. So circumscribed means that your curve is inside your rectangles. And, of course, this is an overestimation because it's hanging out. Now, these were both increasing functions, meaning the function's going up. We don't have to have a graph to know a function's going up. If we look at a table, can't we tell the numbers are going up?
Yeah.
Okay. So if I told you to tell me, looking at a table or a graph, do a right sum and tell me, do a right Riemann sum and tell me if it is over or under estimation, you would first have to think about, well, when it's an increasing function, which one of these do I have? So it's something you just got to memorize, okay? That when it's increasing, it's under with left and over with right. Because the left corner of your rectangle is going to fall below your curve when it's an increasing function. Now, let's look at a decreasing function and see how that relates. And we'll see if I can't pull that to the top so we can do decreasing right here and be able to look at both. Oh, I left an A out of that word. Y'all didn't even tell me.
I didn't even notice.
Well, that's because it's, you know, if you're just missing a little something, sometimes it don't look misspelled to us because we're so used to,
Looking at it.
yeah. All right, so we're going to take and talk about a decreasing function. So I'm just going to reverse what my graph's doing and make a curve going downhill like a half a parabola or something. I'll tell you what, I'd like to make that a little bit shorter than, and maybe not quite so curved. That looks a little too curved. It may not do what I want. Let's do it like that. All right, so first of all,
So we don't put it all the way to the
yeah, don't put it all the way down because I don't have it all the way down for a reason, I'm sure. I probably didn't know what to do with the rectangle on the end. All right, so if I start with an inscribed or circumscribed thought, I don't know whether it's going to be which one, first of all. So I just go up here and take the first point and think about making a rectangle. And then take the next point and think about making a rectangle. And then take the next point and think about making a rectangle. Does everybody see what I'm doing? I'm using the left corner of the rectangle to touch the curve. So by starting up here at the top, I don't have a whole lot outside. And that first rectangle was a little big. But they're really supposed to all be even. I just can't draw it that way. But the key is, when I started on the left corner to make my rectangle, then I had to come down a little bit to hit it the next time. It doesn't really look that way much, but I did. Well, maybe I can clean that up a little bit. This cord's going to be the death of me today. I keep touching the too tight to me. Does that make sense? I had to come down a little bit before I could touch the left corner on the curve.
Yeah.
All right. So the key here is, because it's decreasing, the first one hangs out. So all the rest are going to have to hang out because you're using the left corner. So that makes this one circumscribed and an overestimation. Everybody agree? So let's look at this same thing with using the other corner. See if I can get the curve Well, I didn't get the curve with it, so let me try the curve. All right. So now we're going to use the left corner of our rectangle on the curve. And so when we do that, excuse me, the right corner. When we do the right corner on the curve, then the first one's not going to have all the way to the top, is it? And then when I make my next one, it's going to have a little under. And as they come down, they get more so. Does that make sense? That they're all going to be under because the right corner of your curve is lower than the left corner. See, the left corner is really high, but the right corner touching the curve's got to be lower. And so that causes it to be an inscribed underestimation. So they'll write the opposites of each other. So you got to remember, increasing lower is under, decreasing lower is over, and the rest just switch. So just memorize one of them. Just memorize what left does, and you know the right does the opposite. Does that make sense?
Yeah.
So increasing left is under, and decreasing left is over. And the others do the opposite. So you could just write it down and then write what the right ones would do. Does that make sense to y'all?
Yeah.
Okay. So that's just something you can memorize. All right. Now, we're going to go back and we're going to start looking at some examples of problems. So I'm going to pause the video for just a minute so I can hand this out. So we have pasted this down in our notebook because this is a worksheet that I've just cut apart for our notes. And they'll have an A, B, a C, or sometimes D, sometimes less. But each one of them is going to focus on how to take a table and hand calculate this. Once you set up the hand calculation, you can use your calculator to do some of it. But it's not something I can just type in the calculator and get the answer. All right. So let's talk about a left Riemann sum. First of all, to do this particular problem, looking at the notation here, they want me to integrate from 0 to 120 f of t, where t is time given up there from 0 to 120 by 20s. Now, how many intervals do you see there? How many different sets of intervals across the table could I make? 6, because I go 1, 2, 3, 4, 5, 6. Does everybody see that? You got to come up with the n yourself. They don't tell you the rectangles. They don't tell you how many rectangles you have. So you just count how many sets of 2s would it be, and that'll be your n. So we now know that in part A, n is equal to 6. So let's find our delta x. 120 minus 0 over 6, excuse me, is that right? Yeah, over 6 is 20. No longer do we not know n on the bottom. We now know n because we can count. Because we have all the points we need to do the math. Does that make sense on why we know n? Everybody sees that? 1, 2, 3, 4, 5, 6 sets of numbers. Okay. Now, to do the actual notation, to integrate from 120, 0 to 120 of f of t, let's talk about the actual math that you're doing. It is the height of the function times the width. Now that's pretty simple. It's y times delta x every time. Because to do this, f of t means, okay, got a ghost? F of t means y, right? So there's your hint that's all about y, and that you multiply it by the width of the rectangle, which is what delta is about. Now, let's write that over here. gosh, that if we're doing from 0 to 120 f of t, we are going to do the sum of f of t times delta x. And technically, I guess that really isn't delta x. I guess that's delta t. But we know it is delta x, so I'm just putting it on there that way. Because who knows what letters they're going to put over here.
Yeah.
That's times. Times. So, we're going to do f of 0 times delta x. Because we're doing a left Riemann sum. So when you do a left Riemann sum, you're going to start with the first point because that's going to be the left corner of your rectangle. Tell you what, I want to do this a different way. I'll show you a different way. Let's put delta x on the outside. Let me explain why. If I'm doing every one of them by delta x, I could just do that at the end, right? Mm-hmm. Think of it. Now, when you do it a left Riemann sum, you don't use the last one because you're using the left corner of each set of numbers. Does that make sense? If this is a set of numbers, which one's on the left? 0. If this is a set of number, which one's on the left? 20. So when I get to this last pair, which one's on the left? 100. I don't use the last one. Does that make sense to everybody? Now, the reason I'm showing it like this instead of actually putting the delta x times each one is because that's just a shorter way of writing it. Because think about it. If I had a delta x on all those, couldn't I take a delta x as a GCF?
Yeah.
So it's just easier to write this way because the delta x for all of them is the same. Now, if the space between your x's or t's or whatever your variable for your domain is, if they're not the same, then you're going to have to put it next to each one. For example, if the first one went up by 20 and the next one went up by 30, then I put times 20 on one and times 30 on the other because they don't have to be equal. So we have 20 to be multiplied by 1.2 plus 2.8 plus 4.0 plus 4.7 plus 5.1 plus 5.2. Now, I am trying to show you how you have to write the work. Let me erase this over here. This is how you have to write the work for the AP open-ended part of the test. You have to show a generic formula and what that generic formula means, and then you have to show the numbers plugged in, and then you can do all the math on the calculator if you need to, or in your head, and just write a final answer. They don't need to see the steps between here and how you get there.
They just need to see if you know what you're doing.
Right. They want to know, do you understand the concept of what the variables are standing for, and do you know how to write the correct numbers down to do the math with? After that, you just do the math and you get the answer and you're done. So, what's the answer to this question?
460.
460. Now, sometimes they might ask you, if this was a word problem, they might ask you to explain that answer in the context, but this is not a word problem, so we don't have to do any explaining. We just do a calculation. Now, let's show the same thing with a right Riemann sum of 6 subintervals. So we still have n is 6, so our delta x is still 20, because the space between all the numbers is 20. So how is mine going to be different? That's correct. You don't use the first one. You start off with 20, and you work your way down to the last one, which was at 120. Well, not equal. Close. Almost don't have enough room for that. Well, I can't get my bracket on over there, but oh well. So then I put my 20 in here for delta x, and I put my numbers down. I'm going to cheat. What was the last one? What's the last Y value on your table?
4.8.
4.8. So the key is, it's almost exactly the same calculation, except you take off the first point and you put on the last one. And this will be a right Riemann sum, because I'm using the right of the two pairs of numbers each time.
I got 532.
Now when I do this, y'all, I just take that first number off and change it to the last number. I don't actually physically put it on the end, because you've already got it typed in your calculator. You could just fix that first number. But in my paper, I write it down the correct way. Did anybody else get 532?
Yeah.
Alrighty. So, let's go back and let's look at our data. Does this data increase the whole entire time? Almost does, though, doesn't it?
Yeah,
Almost till the end. So, except for that last value, and we don't use the last value for a left, correct?
yeah.
So, this problem is increasing, and we did it with a left. That means it's under or over?
Over. Yeah. No, it's under.
It's under.
Yeah.
Because remember, the left one doesn't use the first point, so it always has 0 for the first point. I'm assuming the left uses the first point.
Yeah.
But the first point usually is really low. Like this is really low. And it has, so it will be it'll be underneath the curve. So, and it's a little tricky when they do have something like that on the other end, because the right Riemann sum is still an increasing function. So it really should be an overestimation, but it did come out more, didn't it? The right one came out more. All right, so now we're going to do midpoints. Now, midpoints are a little tricky. Because I don't have data for midpoints, do I? Well, let's see. It only asks for 3 subintervals. So, in order to make these sets of 3 subintervals, I should do that in a different color. It doesn't mean I'm using 3 numbers. That does not mean what subintervals are, y'all. Subintervals means I divide my list up into 3 sets of numbers. And when one number stops, the next one begins. Does that make sense?
Yeah.
So since pairs of them made 6 subintervals, I thought I might need to put more numbers together to get 3 subintervals. And so I tried putting 3 together to see if I could just come out with 3 even subintervals, and I do. So I'm going from 0 to 40, and then I'm going from 40 to 80, and then I'm going from 80 to 120. Does that make sense that that's 3 subintervals?
Yeah.
Each one of those has a midpoint.
Is it like the 20 and the 60 and the 100?
Uh-huh. So that's why they had to go with less points, so there would be a middle point in each interval. Okay. So for part C, to integrate from 0 to 120 f of t using midpoints and 3 subintervals, our delta is going to have to change, because now n is equal to 3. So delta x is now 120 minus 0 over 3. It's going by 40s. Does that make sense?
Mm-hmm.
So here's a clue. Find your delta first, because you knew it was 3 subintervals. They told you that. That's what this over here is for. This is all over here because it's n. Okay? Since all that over there tells you n, you could calculate this, learn it's going up by 40s, and then you'd know how to break your table up. Because 0 to 40, 40 to 80, 80 to 120 already broke it up for me. I didn't have to visualize that. I didn't have to guess that or anything. It tells me go by 40s. Okay? So do your delta. It helps. So now my delta, since it's the same every time, I'm going to use certain points that are in the middle. So I'm going to use 20. You said 60 and 100 earlier. And that was correct. Those are the center points of each set, which is why I did them in color so it would be obvious to see. And this should be more accurate than the last two.
I got 508.
Anybody else getting 508?
I'm still working.
Okie dokie. Yeah, that would have been helpful if I had went ahead and wrote that out. You'd have been halfway there. So again, we're showing the work that it takes to show for AP right now, so that you can learn how to not just do the math calculations, but the nomenclature as well. I guess is that the right word?
I got 508.
Okay, 508. All right, so now that's what we already know how to do, but I'm showing it with a table instead of showing y'all how to do it with a function, okay, because we did it with a function earlier. So now we've got to learn trapezoid because we don't know that one. Okay, let's go back and let's think about what is a trapezoid, okay, and let's talk about how do I relate this. See, left, Raman sum, and all of that, and the midpoint, they all use rectangles. Trapezoid rule is called the trapezoid rule because it uses trapezoids. As an example, well, this is increasing. It uses 2 points on the curve and puts that slanted side of the trapezoid that would be on a right trapezoid. These are right trapezoids. You know what a right trapezoid is? Like that?
Yeah.
Okay, it's taking that slanted side and putting it in here, and there's very little wasted space. There's a little bit, but there's very little. And I can't show it because every time I do it, my curve's too straight. Well, you get the idea.
Yeah.
So it'd be like a little space like that.
Yeah.
Okay? So to do that math, instead of doing length times width or height times width, you're finding the area of the trapezoids. See, that's what you were doing earlier with rectangles. You were doing how tall is the rectangle Y times how wide is the rectangle delta X. That was area. You're finding the area. You were doing a geometric area of each one of those pictures. Okay? For me to do that with this, I've got to find the area of a trapezoid. So let's take the area of a trapezoid formula and relate it to the nomenclature here so you can see how it works. So area of a trapezoid is 1/2 times the height times B1 plus B2. So is everybody with me on that? Now, your height is here on normal trapezoid, and B1 is this, and B2 is this. Everybody agree?
Yeah.
But when I turn it, my height is on the bottom, that's right. And that's delta X.
So would that be like 20?
Mm-hmm. Well, no, because we're going with 3 subintervals again.
Oh, okay.
So that's delta X. Then B1 and B2 is the two sides here. It's height, how long those segments are. So you're going to use 2 of the Y values with delta X and 1/2. And every trapezoid in your picture is going to have a 1/2. It's going to have a delta X, but these two numbers are going to be different every time. So we can put these two things outside of our picture, and we can put these things inside the big bracket. So let's go over that. What would the, let me get rid of all this down here. All right, so if I'm integrating from 0 to 120 f of t, I think it's interesting they don't have a DT on that. Do y'all find that interesting?
Yeah.
I don't know. You're going to have a 1/2 out here, and right here, you're going to put in delta x. Now, we're still in 3 subintervals. What was the delta x we had in the last question? Is the same for this question. 40. Then, we are going to put in sets of 2, the 2 values that are in that subinterval is y's. But first, we're going to say what x's cause that. So when we look at this first subinterval from 0 to 40, we're going to put 0 and 40's answers because they're the furthest on the ends. That's the 2 sides. So we're going to do f of 0 plus f of 40 because that's your y values for the first set. The longest it is on one end and the longest it is on the other end for the height. And then you're going to do the next set. You're going to do f of 40 and f of 80. And then you're going to do the next set, f of 80 plus f of 120. And I know it reuses a value there, but that's what the height of those rectangles is because this rectangle's B2, it becomes B1 of the next one. Does that make sense for this trapezoid? All right, so now we're going to do 1/2 of 40 is 20. We could go ahead and simplify that and put in whatever those numbers are. So if I got them written down. Oh, yeah, I do. Well, no, I don't. I went ahead and added them together, so I can't do that. So y'all fill them in and add them up. Multiply it by 20. Why am I doing 20?
Because that's your 1/2.
Right. Right, I went ahead and did delta x times 1/2. Now, in your AP work, you wouldn't write that delta x under there. I just wrote that to remind you that's what it was in your notes. But you would just write out the problem. In fact, you might first put the delta x in the parentheses, like right here. And then you'd say 40 times 1/2, put your 20 in. And if you show all your work of where you got your delta x's from and everything, then they're good with you just doing some math and putting the answer down.
I got 484.
484.
Yeah.
And that's better than the others, isn't it?
Yeah.
Trapezoid's more accurate than midpoint. So that means that if I can do trapezoid, it'd be worth it. Alright, so now,
But, what was our A? The left Simon?
okay, so left Ryman was 460, right Ryman was 532, the middle was 508, and so now we're saying by using trapezoid, it's 484, which is closer to the right answer for the exact.
Oh, okay. I just didn't know. Yeah.
We can't.
So
That's why it's important to know which one gives you the best answer. Now, if I could do Simpson's with this problem, it would be more accurate because Simpson's rule is the most accurate, but you have to have n as an even number, and n wasn't an even number in this problem.
Is there a point in using like Ryman's if trapezoidal is more accurate?
Well, in some respects, the Ryman sum didn't use that one value that wasn't increasing for the left, and so that might make it just a little bit better sometimes, but we just have to use whatever they tell us to use because they always tell you what they want you to use. They at least don't leave that up to us a lot of times, but if they don't tell us and we've got the information and can do trapezoidal, it's better. All right, so I'm going to give y'all a slip. You're going to paste it down and you're going to do one on your own, and then we'll check it. All right, so looking at this left, right, and trapezoidal sum for 4 subintervals, what we discovered was this problem is different because it doesn't go up by 40s or 20s all the way through. It goes up by a different amount between every set of numbers. And so instead of putting delta x in front of the whole problem, you had to put delta x with each function's y value because of it being different. So in the first subtotal from 0 to 40, the left corner of your rectangle is 0, so we take the y value f of 0 times 40 because that's the distance between 0 and 40. Or in the case of 40 to 70, that's 30 up. But if we use the left corner, we'd use the value of 40 at for the function 180 times 130. Excuse me, times 30. And so you do that with each one. With B, the difference between A and B is A uses the first point because it's the left point, and B is using the right point every time, so it doesn't use the first one at all. It uses the last value, 100. And then to do trapezoidal, you'll have your half out in front, but it won't be with your delta x. Since delta x is changing each time, you put delta x in with the sum of B1 plus B2 for your trapezoid. So we're working on a worksheet that goes along with this, and on the worksheet there's one every so often that says Simpson's rule, but there weren't any Simpson's rules in these first two problems, so we'll come back and we'll do a Simpson's rule in our notes first before we move on to looking at word problems and graphs on Monday. Hope this helps you, Jacob.